Hello, everyone. So we want to continue talking about heat exchanger and heat exchanger analysis. So up to now, we talked about the calculations of the overall heat transfer coefficients and the overall heat transfer inside heat exchanger. So now we want to talk about another aspects of heat exchanger analysis. Typically, when we focus on heat exchanger unit, we are interested in the heat exchangers that will gives us certain temperature change across the heat exchanger. And for that temperature difference tells us what temperature difference between the hot fluid and cold fluid in average should be. So simply, we are looking for heat exchanger that gives us, for example, for a certain cold inlet of the fluid flow gives us certain temperature at the outlet, or for a certain hot flow inlet gives us certain hot flow outlet. So temperature is very important to us. And these temperature difference are correlated somehow to mean or average temperature difference between the hot side and the cold side. It is very important. Obviously, as you know, the driving force for heat transfer is temperature difference. It means if you have higher temperature difference between the cold side and the hot side, you're going to get better or higher heat transfer rate. So one of the methods of the analysis of heat exchanger is looking at that mean temperature difference between the cold side and the hot side, and it's calculated as a log mean temperature difference, or LMTD. LMTD method is very useful method in engineering applications in designing and investigation of the heat exchanger. The other method is effectiveness NTU. In this lecture, we're going to focus on log mean temperature method. So how this works? Look at this typical and standard form of heat exchanger. We have tubular heat exchanger. We have parallel flow and counter flow, or shell and tube. Okay, so what is the heat transfer in the cold side? The amount of heat transfer is mass flow rates times the specific heat of the fluid at the cold side times the temperature difference. This is the total thermal energy change inside at the cold side. What about the hot side? We have similar equation. As long as we don't have a phase change and we only have temperature difference, we have temperature increase or decrease, then these two equations gives us the amount of thermal energy change in each side. Okay, what are those? M dots are the mass flow rate at the cold side and the hot side. M dot sub C means cold side, M dot sub H means hot side. C sub PC is a specific heats of the cold fluid, and C sub PH is the specific heats of the hot fluid. TC out and TH out are the outlet temperature at the cold side and hot side respectively, and TC in and TH in are the inlet temperature at the cold side and hot side respectively. Also, the multiplication, the product of mass flow rate and a specific heat is called heat capacity rate. So instead of writing m dot times c sub pc or c sub m dot times c sub ph, we write just capital letter c sub h, capital letter c sub e, c. So we can simplify those two equations in to this form. Okay, so these are the heat transfer rate at the cold side and heat transfer at the hot side. If you don't have any loss of energy, and from the heat exchanger to the surrounding, and the only heat transfer is happening between the hot side and the cold side, then these two equations are equal. Okay, they are supposed to be equal if you don't have any heat loss. So whatever that is lost from the hot side is going to be gained by the cold side, and whatever whatever heat transfer or whatever thermal energy that is exchanged is actually exchanged between cold side and hot side. Okay, so these two must be equal in ideal situation, these two. So if you have this value for the cold side, and you know, let's say you know the temperature inlet at the hot side and C sub H at the hot side, you can calculate the TH out at the hot side. Okay, so you can use this equality to calculate any unknown values. And this equality very helpful. So look at these two equations. What does this tells us? It tells us that if, let's say, a specific heat capacity rate at the cold side, if they are not always equal, if these heat capacity rate at the cold side and the hot side are equal, if they are equal, since always these two equations are also equal, the temperature difference at the cold side and temperature at the hot side must be equal, right? So whether you have counter flow heat exchanger or parallel flow heat exchanger, then, and if the heat capacity rate at the cold side and hot side are the same, the temperature difference across the heat exchanger stays the same. Okay, this is for very specific situation when the heat capacity rate at the cold side and hot side are the same, but it's not always the case. So in typical situation, in most engineering applications, we may not have this case. That means the temperature difference between the cold side and hot side can change, can increase or decrease. But if you want to calculate the heat transfer between two fluids, between 2 points, you need some form of heat, some form of temperature difference, some average temperature difference. Okay, unless you want to calculate the heat transfer using these individual equations separately, and they are supposed to be equal, you want to know some temperature difference, because temperature difference, as I said, changes across the heat exchanger. So you're interested in some average temperature difference between the cold flow and hot flow. Because instead of calculating heat transfer rate using these two separate equations that are also equal, ideally, you want to use one single equation. Overall heat transfer coefficients times the area through which heat transfer is happening. And that area depends on the structure of your heat exchanger. If it's cylindrical shape, is it flat plate? So what's the boundary between the cold and hot side? Times some mean temperature, delta T sub M, between the hot side and cold side. This is some appropriate mean or average temperature difference between the two flows of the cold and hot fluids. Okay, so we are interested in knowing this. As I said, these can change across the heat exchanger unit. In this simple case, it stays constant, the temperature difference. But in reality, it changes. It can decrease or increase. Okay, So what is this? This is a representative of temperature, overall temperature difference between the cold side and hot side. And when you have higher mean average temperature difference between the hot side and cold side for a certain unit, you have better heat transfer rate, you have higher heat transfer rate, you have more efficient heat exchanger, you have more efficient thermal energy exchange between two streams of fluids, between the cold side and hot side. So how do we calculate this? So the calculation of this, the derivation of the correlation for that can be done using energy balance between the cold side and hot side. As I said, the cold side, whatever energy is gained at the cold side must be equal to whatever energy that is lost at the hot side at each section of the heat exchanger. So if we perform that energy balance, this is the equation that we get. And it's called log mean temperature difference between cold side and hot side over certain lengths, whatever lengths that we are focusing at. Delta T sub 1 minus delta T sub 2 over natural log of delta T sub 1 divided by delta T sub 2. So what are delta T sub 1 and delta T sub 2? For simple and a standard form and structure of heat exchangers, the delta T sub 1 and delta T sub 2 can be calculated using these correlations. So let's say you have parallel flow heat exchanger. Okay, simple parallel flow heat exchanger. Then delta T1 is the temperature at the hot side at the inlet minus temperature at the cold side at the inlet, and delta T sub 2 is temperature at the hot side of the hot side at the outlet, and temperature of the minus temperature at the cold side at the outlet. So this is how delta T sub 1 and delta T sub 2 is defined when you have parallel flow heat exchanger, a standard heat exchanger. Okay, so the equation is this, but delta T sub 1 and delta T sub 2 is defined as these for parallel flow. What if we have counterflow? If we have counterflow, again, guys, these equations are derived from energy balance equation. It's not very complicated to derive this equation, but I didn't want to just put the derivation in here. It's very simple because we need to be able to just apply these equations that are already derived. So when you have counterflow heat exchanger, that means when the sense of directions at the hot side and cold side are opposite to each other, then the delta T1 and delta T2 are defined differently than the way that we define for parallel flow. Delta T1 is temperature at the inlet of the hot side minus temperature at the outlet of the cold side, and delta T2 is equal to temperature at the outlet of the hot side minus temperature at the inlet of the cold side. So the equation for both the parallel flow and counterflow heat exchangers are exactly the same. The structure of the equation is the same. The form and shape of the equation is the same. The definition of delta T1 and delta 2 are just different. As I said, log mean temperature or logarithmic mean temperature difference is an exact representation of the average temperature difference between the hot and cold fluids. Why do we use this again? Because we don't know, because the temperature difference across the heat exchanger changes between hot and cold fluid, and we need to know some average temperature difference. Look at this section, for example. The temperature here of the hot side and cold side have some differences. There is some difference between temperature at the hot side and cold side. Here, at this section, the temperature difference between the hot side and cold side are another value, and these two are not the same. So the temperature difference across the unit changes. The same for here. That's why when we want to write the heat transfer rate, calculate heat transfer rate between two flows using one unique equation, and we need to have some overall average temperature difference over an entire unit of heat exchanger, we need to use these equations. This is very, this is actually used for a standard form of heat exchanger, okay? Because not all the heat exchanger that you see in the industry are following the same structure that you see. I mean, these kind of, the standard form of heat exchanger has so many applications in industry and power plant, but you don't see only this form of heat exchanger. So when you want to investigate and analyze the more complicated heat transfer heat exchangers, then the delta T log mean temperature, delta T log sub Lm, is not following exactly this equation. I mean, you can use this equation, but you need to multiply it by some correction factor. So you need to incorporate some other factors to make it work, make this simple equation work for more complicated form of heat exchangers. And there is some important notes about the difference between counterflow heat exchanger and parallel flow heat exchanger. The variation of the fluid temperatures in the counterflow heat exchangers, counterflow double pipe heat exchangers, is not exactly the same as the variation of fluid temperatures between the cold side and hot side in double pipe heat exchanger with parallel flow. There are some differences, okay? And in average, overall, in a counterflow heat exchanger, we have higher. So let's say you have the same, you have the same structure in terms of the length and the area. And you have the same inlet at the cold side and the hot side. If instead of parallel flow, you arrange a counterflow for that heat exchanger, for double pipe, for example, the log mean temperature is going to be larger than the log mean temperature for the parallel flow arrangement. And this is very good. So for the same length, for the same unit, and for the same inlet of the hot and cold side temperature, for the counterflow arrangement of the streams, you get higher log mean temperature, or basically higher and larger value of average temperature difference between the cold side and hot side. And this is very good. It means you have better and higher driving force, larger driving force between the hot side and the cold side, heat transfer between hot side and cold side. So it's good. It means you can use a smaller value, or in other words, you can use a smaller heat exchanger for the same rate of heat transfer. So when for the same inlet of the hot side and cold side in counterflow, you get better overall average temperature difference between the cold side and hot side, then it means you can achieve the same amount of heat transfer for a smaller length. So you can build a smaller heat exchanger. So that's the benefit of counterflow heat exchangers. And typically in industry, in any applications, although the arrangement and the geometry of the heat exchangers are going to be more complicated, especially for compact heat exchangers, they try to arrange a flow streams in the cold side and hot side such that it's sort of similar to some form of counterflow heat exchanger rather than parallel flow heat exchangers. So we try to make heat exchangers counterflow heat exchangers, no matter what type of what form of heat exchangers that we have. Because as I said, the form of heat exchangers, the shape of them can be more complicated than this, and they are. Heating water in a counterflow heat exchanger. A counterflow double pipe heat exchanger is to heat water from 20 degrees Celsius to 80 degrees Celsius at a rate of 1.2 kilogram per second. The heating is to be accomplished by geothermal water available at 160 degrees Celsius at a mass flow rate of 2 kilogram per second. The inner tube is thin-walled and has a diameter of 1.5 centimeter. This information is very important. What does that mean? It means the inner diameter and outer diameter of the tube are almost the same. It means the wall of this tube, this inner tube, is very thin and it does not impose any thermal resistance against conduction. So there is no resistance against conduction at the boundary between inner flow and outer flow, between the cold side and hot side. So we don't have to account for the thermal resistance against conduction as a result of having cylindrical wall of the pipe. If the overall heat transfer coefficient of the heat exchanger is 640 watt per meter square Kelvin, what is the length of the heat exchanger required to achieve the desired heating? So we have inner temperature, inlet temperature at the cold side, inlet temperature at the hot side, outlet temperature at the cold side, and it seems like we don't have outlet temperature at the hot side. We have the diameter and we are asked to calculate the overall length of the heat exchanger. So we take the specific heat of water and geothermal fluid to be 4.18 and 4.31 kilojoule per kilogram respectively. Okay, so you need to read the properties, thermophysical properties of the fluids. So for water, to read the properties, we can read it at some mean temperature. At the inlet, it's 20, at the outlet is 80 degrees Celsius. So mean temperature is around 50 degrees, right? So at 50 degrees Celsius, you read the specific heat of the water and is around 4.18. For geothermal fluid, if you search for it, and we assume that its temperature does not change significantly, but it may, at around 160, 150, 120 degrees Celsius, its specific heat is around this value. So I got this value from the book. So this is the value that book gave me for geothermal fluid. So we have the specific heat. Now, we have all the information for the water side, for the cold side. So we can calculate the heat transfer. M dot of the cold side, C sub P, a specific heat of the cold side of water, that is 4.18, and temperature difference. And this value is exactly the same as the heat transfer rate that can be calculated from the hot side equation. So they must be the same, but for the hot side, we don't know the outlet temperature. So we set this 301 equal to this, and the outlet temperature of the hot side is derived as 125 degrees Celsius. Okay. So this is the specific, this is the temperature outlet at the hot side. Now, we have a counterflow heat exchanger. So for counterflow arrangement, we know that delta T sub 1 for the calculation of log mean temperature, the delta T sub 1 is TH, T hot at the inlet minus T cold at the outlet. For delta T2 is T hot side at the outlet minus T cold at the inlet. So we have these and this equation, we plug them into this equation and we get the log mean temperature. As I said, this is counterflow heat exchanger, so that's why we use this definition for the calculation of delta T sub 1 and delta T sub 2. Then the surface area of the heat exchanger is determined to be 5.12 because this heat transfer, the heat transfer that we calculated in the previous slide, 301 kilowatt or 301,000 watt, is equal to overall heat transfer coefficients times the area through which the heat transfer is happening times the log mean temperature. We already have the log mean temperature. Overall heat transfer coefficient is given, and Q dot is also calculated in the previous slide according to the information that was given for the cold side. So the area is calculated. Area itself is equal to, is a cylindrical pipe, right? So area is pi diameter times L, and from this we can calculate the length of the heat exchanger. And this problem is assigned to you as a practice problem. A double pipe parallel flow heat exchanger is used to heat cold tap water with hot water. Hot water with the specific heat of 4.25 kilojoule per kilogram Kelvin enters the tube at 85 degrees Celsius at a rate of 1.4 kilogram per second and leaves at 50 degrees. So inlet and outlet of the hot water is given with a specific heat. The heat exchanger is not well insulated, and it is estimated that 3% of the heat given up by the hot fluid is lost from the heat exchanger. So part of the thermal energy of the hot fluid is lost, the surrounding. If the overall heat transfer coefficient and the surface area of the heat exchanger are 1150 watt per meter square Kelvin and 4 meters square, what is the rate of heat transfer to the cold water and the log mean temperature difference for this heat exchanger? So this is your assignment. Thank you very much and have a great week.